Let's look at a line integral. Many times when we compute line integrals, the path is actually piecewise smooth. That is, it has some corners. So that usually takes a little bit more work. But say, for instance, we have a triangle with vertices 0, 0, 1, 0, and 0, 1, and we want to traverse this path in a counterclockwise method. So what we want to do here is parameterize each of the pieces. And since these are line segments, they're not too difficult to do, but I want to show you a technique to get a nice parameterization which you can use often. So for C1 here, which I've labeled, that's the easy one. We can just have t in the x-coordinate, 0 in the y-coordinate, and t can run from 0 to 1. So that's a basic parameterization there. Now for C2, the first thing we do is we want the direction of this, so we take the difference in the vector 0, 1, and 1, 0. That is thinking of the points as vectors, and we get negative 1, 1. So that provides the distance. Now we want to start at 1, 0, but in order to get our parameters to run consecutively, we're going to replace t with t minus 1 to give us the necessary translation. So now we start at 1, 0, then we have t minus 1 times the direction negative 1, 1. And that will give us 2 minus t, comma t minus 1. Notice when you multiply here, you get an additional copy of 1, and 1 plus 1 gives you the 2 here with the negative t. And now t can run from 1 to 2. Notice when t is equal to 1, we get 1, 0, and t is equal to 2, we get 0, 1. So we get the exact path with the consecutive parameter values, which makes the parameterization look more clean and more efficient. Now for the third part, let's do the same thing again. Let's get the direction. So we'll take the vector 0, 0 minus the vector 0, 1 and get 0, negative 1. And then the R3, that is for this particular part of the parameterization, we start at 0, 1 and do the same thing again, replace t with t minus 2 and then multiply by the direction. In this particular case, the x-coordinates are all 0, but then of course here, if you notice, we're going to get a negative, negative, a positive 2 plus a 1 to give us a 3 here, and then the minus t, and then t can run from 2 to 3. So that gives a nice clean parameterization. So what we can do is take all these pieces and put them into one parameterization. Notice you label everything with subscripts. That's how you can keep up with things. So now our parameterization R of t will be t comma 0 when t runs from 0 to 1, 2 minus t comma t minus 1 when t runs from 1 to 2, and then 0, 3 minus t when t runs from 2 to 3. Now, because when we do these types of line integrals, we need the speed, we can go ahead and compute the actual velocity of the curve. These are easy to do. We get 1, 0, negative 1, 1, and 0, negative 1, differentiation with respect to t. And then the speed here, we just take the magnitudes. So of course here we'll get 1, here we'll get square root 2, and here we'll get 1 because we need those in our definition of the line integral. Now, for instance, all of this work will allow us to compute this integral about C. And notice C is the union of all three of these segments here. So we've got a piecewise smooth curve. So when we integrate this particular integrand along C, we just do the separate parts. So for C1, we do the composition. That is, we replace x with t and y with 0, and that just leaves us with a t. And then, of course, the speed is 1, so you don't see that dt. And then we just get a very simple add 1, divide by the new power, 1/2 t squared between 0 and 1, and we get 1/2. Okay, well, let's look at C2, this part here. So we do the composition again. X is replaced with 2 minus t, and y is replaced with t minus 1 to give us this integrand. And of course, t runs from 1 to 2. Now these are easy, add 1, divide by the new power. Of course, we need the negative here. by the chain rule. So we get the negative of 2 minus t squared divided by 2. And here add 1 divided by the new power. We get 7 times 2/3 t minus 1 to the 3/2 power. And then of course we evaluate from 1 to 2. Now notice when we substitute the 2, that zeroes out, but we get a 1 here, so that just gives us a 7 times the 2/3, which is a 14 over 3, excuse me. Then we subtract with the fundamental theorem. This of course will zero out, but this will just give us a 1/2. So we have minus the negative 1/2, and that just gives us, of course, and now I haven't mentioned this, we have the speed of the curve here, square root 2 that we have here, so that does make a difference, and I went ahead and factored this. So the speed we need. So we've got the square root of 2 times 14 over 3 minus the negative. So we can just get a common denominator of 6. That'll give us a 28 plus 3 in the numerator. We add, we get 31 over 6 times the square root of 2. But just remember, when the speed is 1, it's easy to forget about it. But of course, when it's other than 1, it turns out to be quite important. So remember the speed from the definition of line integral. And again, we'll say more about this as we actually start doing some similar problems with different hypotheses. Now, for the third part, we do the same thing. Again, we replace x with 0. That zeroes this out. And of course, we replace y with 3 minus t. So we get the integral from 2 to 3 of 7 times the square root of 3 minus t. Again, that's add 1 divided by the new power. But of course, we need the negative here from the chain rule. So that's going to give us a negative 14 over 3. When we evaluate at 3, we zero out. But when we evaluate at 1, we just get 1. But the minus from the fundamental theorem, minus minus gives a 14 over 3. And so now to finish the problem, that is to do this integral here, we simply add all the components. So the integral about the entire curve of x plus 7 times the square root of y, we add 1/2 plus 31 over 6 root 2 plus 14 over 3, which you see right here. Again, we get a common denominator, and we get 31 plus 31 root 2 over 6. And then if you want to factor it, you can. So the final answer will be 31 times the quantity 1 plus the square root of 2 divided by 6. Now remember, these are scalar functions. So we have to be very careful that when we're doing these scalar line integrals that we remember the speed. It's often very easy to forget. And we are done.